Hi, this is exploration. This is part 5 of our exploration into Lagrange's theorem. Into Lagrange's theorem. This is part 5. Alright, made a mistake there. Okay. So this is part 5 of this exploration. Alright, so well, pretty simply, what's Lagrange's theorem saying? Lagrange's theorem is saying the following. Suppose we have some group G, right? We're going to say that this group is finite. Suppose we have a finite group G and we pick a subgroup H of G, okay? So, what's the relation between the cardinality of H and the cardinality of G? It turns out that Lagrange's theorem is telling us that the cardinality of H must divide the cardinality of G if G is a finite group. That's, of course, we're saying that H is a subgroup of G, right? So this is what we've been exploring in the last couple of videos, and our strategy has quickly morphed into working with what we're calling cosets, left cosets, and in particular we came upon the following idea in the last video. We said the following: well, if we had G, our group G, and we called our group, let's say it had the elements alpha 1, alpha 2, well, let's just call them G1, G2, why not, right? So let's for once follow some conventions. So let's say we have a group G equals to G1. Where's the hard eraser? All right, hard eraser, here we come. So let's say we have our group and it has the elements G1, G2, G3 up to, let's say, some, what do you want to call it? GM. Okay, let's call it GM. Our group is finite, so their number of elements can be counted. In this case, we are saying there are M elements in our group G. Okay, well, and let's suppose that H is some subgroup. Nobody said anything about being normal. Let's suppose that H is some subgroup of G, right? So what we came to the conclusion before is, well, you know, maybe we can partition G. We could break up G as follows. We get our group G and we can partition it into partitions. One partition being partition 1, second partition being partition 2, etc., up to some partition K. And we're thinking about the following idea. Suppose we could guarantee the following conditions. Condition 1, that each pi, right, each of the partitions is actually equal. Okay, another error. Each of these partitions is actually equal to a left coset of H, right? So equals to G, let's say GIH for some GI element of G, elements of the group, right? So we're saying each of these, if we can guarantee that each of these partitions is actually a left coset of H, and if we can also guarantee the second condition that, well, every element, every GI element of G, every element of the group is such that, if we can guarantee that every element of the group is such that GI is some element of one of these partitions equals to PI, right, is an element of one of the partitions, let's call it PI, right? So if we can guarantee this, then we can also make the following conclusion. And this is the second condition. That is, what we're saying here is that we can't find any group element that's not one of these partitions. Every group element is in some partition. And furthermore, we're going to require that the partitions are pairwise disjoint. That is, Pi intersect Pj is empty for any I not equal to j. If we get any two partitions and take the intersection is empty. That means that if, let's say, we got some group element Gi and found that it was in one of these partitions, let's say it was in partition P2, well, it can't be in any of the other partitions. That is, every element belongs to one and only one partition. This is what we're trying to guarantee here. And the idea we came up to last time was that, look, if we can actually prove these three conditions, right here, if we could prove this, that these three conditions are true, would be able to conclude that the sum of the cardinality of the first partition plus the sum of the cardinality of the second partition plus, actually, sure. We'll be able to sum up the cardinality of the first partition, cardinality of the second partition. If we sum the cardinalities of all these partitions up to the cardinality of the, how many partitions did we have? We had k partitions. Up to the cardinality of the kth partition, that the sum of the cardinalities of all of these elements in these partitions is going to end up giving us, well, just the cardinality of G. That was the idea. And from here we said we'd be able to conclude that the cardinality of H times some m natural number, m integer, in this case it would just be a natural number, m natural number must equal the cardinality of G. And if we can conclude this, we'll be able to conclude that cardinality of H divides cardinality of G, which is what we've been trying to prove. Right? So see if you could see why these three conditions being true implies that the sum of the cardinalities of the partition equal to the sum of the cardinality will equal to the cardinality of the group, and that implies that necessarily the cardinality of H times m, there exists some m for which there exists some m element of the natural numbers for which cardinality of H times m equals to cardinality of G. And why from there we can conclude that cardinality of H divides cardinality of G. For the time being, we're going to focus on proving, right? So we said if these conditions are true, Lagrange's theorem is true. Sure, but how do we know these conditions are true for cosets and for any finite group G? So let's think about these conditions, whether we can actually set them up and guarantee that they're true. Okay, so let's see. Right, so let's say we have our group G again, right? So let's see if we can establish that the conditions 1, 2, and 3 are true. So if our group G has the elements G1, G2 up to Gm, okay, it's finite, and H is some subgroup of G, alright, well, I mean, we can create a bunch of cosets. So for instance, well, G1H is a coset, okay, G2H is a coset, G3H is a coset, and so on and so forth. Up to GMH, all those are cosets, right? So let's first look at a few ideas here. So these are all cosets, okay? So we want to turn them into partitions, maybe partition 1, partition 2, up to some partition k as we've done before, and we want to show that these partitions satisfy the conditions we're talking about. Okay, well, how are we going to do that? How are we going to make these cosets and turn them into partitions that satisfy the conditions we just looked at before? Well, one thing we notice off the bat is that if we consider all of these cosets, right, we have, how many cosets do we have? M cosets. The question is, are all of these cosets really different, right? Is it possible, for instance, that let's say some GIH equals to some GJH, where GI does not equal to GJ, right? Is it possible, right? So in the sense that, well, maybe we are double counting. Like we could have things that look like different cosets that are really the same coset, right? So okay, and we want to account for that somehow. All right, so how do we proceed with this question? How do we establish these partitions? Okay, first of all, we can establish one condition at least. Our first condition that we're looking at before was this. Our first condition was, well, our first condition was that, uh, okay, let's say a second condition was that every element Gi is in some partition. Okay, so temporarily, let's consider these to be our partitions. So let's call P1, let our first partition equal to G1H. let our second partition equals to, okay, geez, okay. So we made an error here. So, okay, let our first partition equal to G1H. Let our second partition, partition 2, we're going to let that equal to G2H. Okay, G2H. Let partition 3 equal to G3H. And we're going to continue this process and say that partition M is going to be what? GMH, right? You guessed it. All right. So let's call let these be our partitions temporarily. Let's see if these partitions satisfy any of the properties we're looking for. For instance, if we pick some element gi of g, right? Is it true that gi lies in some partition? Right? Let's first start with that question. For gi element of g, is gi element of some partition, some peak, let's say PL, right? Partition L. Well, what do you think? Is this true? Well, the way we've labeled, right? So the way we've labeled, okay, if you think it's true that some GI lies in one of these partitions, could you think of a partition that GI actually lies in? Alright, so G sub I, right? The way we've labeled the partitions, we have the following condition. Partition I, the partition corresponding to the element GI, partition I has been chosen to be G sub I H, right? G sub I H. Well, what are the elements of G sub I H? Well, G sub I H is really equal to, well, all the elements of H. Let's say H has the identity. It may have some other element. Let's call that H1, H2, up to whatever the cardinality of H is. Let's say H has cardinality R, HR. Right? So, I mean, that's what H is. So GH then, GIH is just going to be, well, whatever this thing is left multiplied, every element in H left multiplied by GI. So now what would be the elements of the coset GIH? Well, that would be GI, GIH1, GIH2, blah, 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 right? Okay. Up to, let's say, GIHR in this case. Okay. Right. So this is what our partition, this would G, so notice, is GI an element of this partition? Well, of course, we have GI over here, right? So because H has the identity element, left multiplying the coset created by GI is going to give us some GI, is going to guarantee that GI is an element of the coset GIH, which means that, and this is true for any GI element of G. So what that means is that we've established one of the conditions. At least this, let's write the conditions that we've established in red somewhere. What the heck? Yeah. Okay. So every condition we establish, we're going to write in red. So let's put them somewhere on the side of our board here. Let's go there. Okay. So these are, let's put them in a different color just to make them special somehow. So far we've concluded the following. Well, each GI element of G is in some partition. All right. Now all we need to do is to check the other two conditions. All right. So okay, let's go back to black. All right. Another condition that we need to check about these partitions is, well, okay, fine, we've created all these partitions, but we've said that every element of the group is in one of these partitions. The other thing we had to check is that the partitions are pairwise disjoint. Another thing we had to check is that, what was the other thing we needed to check actually? Well, every element of the group is in one of these partitions. The partitions are pairwise disjoint. And what else? What else? What else? Oh yeah, each partition is of the form, the other condition we had to check is that each partition, each pi, each partition pi is equal to some coset. Okay, so each partition pi equals to some left coset. Well, is that true? Well, clearly it is, right? By definition, P1 was defined to be G1H, P2 was defined to be G2H, P3 was defined to be G3H. So indeed, each partition equals to GIH. So each partition is actually a left coset. All right. So this is turning out to not be as hard as we thought it would be, right? So far we've established two conditions. Each GI lies in some partition. We've also established, okay, now let's get our orange color back. Why the heck? Let's be consistent. Each partition Pi is such that Pi equals to GIH, some left coset, right? Some left coset. All right. So we've established the second condition. Now the question becomes, well, are we done? Well, clearly not, right? We have a third condition to fulfill. And the third condition is that each of these cosets, right, is to check that each of these cosets are pairwise disjoint. All right? So, I mean, is this true that the cosets are pairwise disjoint? Well, what would it mean for any two cosets to be pairwise disjoint? That would mean that, yeah, what would that mean? So, each coset, let's say we have two cosets, Pij, right? Pi and Pj, all right? Here, okay, as expected, the pen misbehaves. Okay, so here we're saying that I does not equal to j. All right, that's one of the conditions we're establishing. Now we're saying that what would it take to establish that the partitions are pairwise disjoint? Well, that would mean that for any pi, pj, where I does not equal to j, would need to establish that the partition pi intersect pj is empty. Sorry, is not empty. Sorry, is empty. Yeah, that's right. They have nothing in common, right? So, but what would that mean precisely? Well, it would mean that, remember, our subgroup H is being taken to have the elements H1, H2 up to some H. We picked HR last time. Okay. So what's the coset Pi? Well, the coset Pi is what? The coset Pi is GIH by definition, which will mean that it's the same as GI multiplied by 1, GI multiplied by H1, GI multiplied by H2, all the way till GI multiplied by HR, right? And what's the coset PJ going to be? Well, the coset PJ is going to be GJ multiplied by H, left coset formed by GI on H, and that would just be, well, GJ, GJH, GJH, this was H1, H2, all the way till GJHR, okay? So how can we guarantee that these cosets Pi and Pj are necessarily distinct, that none of these elements, what would it mean for Pi intersect Pj to be empty? Well, think about that for a second. To say that Pi intersect Pj is empty means that none of the elements here is an element over here. How can we guarantee that these elements will always be disjoint, that GIH will always be disjoint from GIH, right? That's kind of hard to say, isn't it? And we did see before in some example, the example we tried an example before where we'd worked with G equals to Z under addition. We'd looked at H equals to 4Z under addition. We'd noticed that H is actually a subgroup of G, which means that 4Z was actually seen to be a subgroup of Z. And we realized the following, that the cosets of G, which otherwise known as Z in that case, the cosets of Z just turned out to be, well, 1 plus, actually just 4Z first, 0 plus 4Z, then 1 plus 4Z, then 2 plus 4z, and then we also had 3 plus 4z. And it turned out that these were the only cosets that we had. In fact, we noticed that a coset like 4 plus 4z actually equals to 0 plus 4z. We noticed that 5 plus 4z, a coset like 5 plus 4z, actually equal to 1 plus 4z. So the idea was, look, okay, we have, if we looked at the cosets originally, we'd have 4z, we'd have 0 plus 1 plus 4z, right? The cosets, right? So again, here the operation is addition. So GH, well, GH is how our cosets are formed. H is the subgroup is 4z, and G is an element of the group. In this case, our group is a set of integers, and we wouldn't say G times H, because our operation here times is addition. We're looking at the group Z under addition. So really, in this case, we'll be writing G plus H. But our H is 4Z, and our group element G is some integer. That's why we're writing things as 1 plus 4Z, 0 plus 4Z, right? But notice, how many integers are there? There are infinitely many. So one would think that we should be able to, 2 plus 4Z would be a coset, 3 plus 4Z would be a coset, 4 plus 4Z would be a coset, 5 plus 4Z would be a coset, 6 plus 4Z would be a coset, and so on and so forth. One would think that this process goes on forever, that there are infinitely many cosets. But we noticed before that this is not true. It turns out that some of the cosets are actually equal to each other. It actually turns out that there are only 4 distinct cosets. And when it came to the set of integers, the group of integers, we realized that these 4 cosets, 4z, 1 plus 4z, 2 plus 4z, and 3 plus 4z, are enough to partition the entire set of integers. That is, every integer is in one of these cosets, and if an integer is in one coset, it's not in any of the other cosets. And the cosets are, of course, of the form, the partitions are, of course, cosets themselves. We've seen that. So this means it's at least plausible that here in the partitions we've been creating, right? So because here's what we've done so far. We've said that, okay, we've said that, all right, we have some space here. If we look at the group G and we take some subgroup H of G, right? So we said that this group G can actually be partitioned, okay? We're talking about, we're creating some partitions here. And our first partition was, well, the group G was taken to have elements G1, G2, all the way up to GR. And we saw that, well, the partitions we formed, we could break it up into partitions P1, P2. These are the partitions we are considering so far, up to PR. And in particular, these partitions, each of them is really a coset. So what we're really getting here is that we're partitioning G as follows. G is being partitioned into the first coset, which is P1, but that's G1H, the left coset G1H. The second partition is G2H. The third partition is G3H. And we're doing this up until we get GRH. This is what we have right now. And so far we found some things that are true. Well, this coset, G1H, G2H, all these cosets, well, all the partitions are cosets. That's one condition. We established that every group element is in one of these cosets, but we're wondering whether these cosets are indeed disjoint. Because if GIH intersect GJH, say, is not empty, right? That means they have something in common where I does not equal to J, then this coset fails to satisfy our condition of a partition. The other condition of the partition was like the intersection of the partition should be empty. So what this means is that, well, we're noticing that it's actually kind of possible. It's plausible that, as we saw in the case of the group Z and the subgroup 4Z, it's possible for you to have infinitely many partitions, or many partitions, and some of the partitions to be equal to each other. For example, 4 plus 4Z was equal to 4 plus 4Z was equal to 0 plus 4Z. 5 plus 4Z was equal to 1 plus 4Z. 6 plus 4Z, right, please verify this if you're confused. 6 plus 4Z was actually equal to the coset 2 plus 4Z, etc., etc. So it turns out that plus. It turned out that while we seem to have many cosets, we really had 4 cosets because the rest of them, many of them were equal to each other. So here, it's also plausible. There is nothing that's guaranteeing that, so far at least, we can't guarantee yet that the intersection of any two of these cosets is not going to be empty. It's quite possible that these cosets, that we take some coset gi, it's quite possible that we take some coset gih, take the intersection with gjh, and find that it's not empty. There's some element in this intersection, right? It's not empty. That's possible. That's quite possible. So does that mean we're screwed? Does this mean that this partition won't work? Yes, that's what it means, right? This partition will not necessarily work. Okay, but is there a way we could modify these partitions so that we end up maintaining the conditions already established, that every group element is in the modification of these partitions and every partition is still a coset, and also somehow guarantee that in this new modification of these cosets we actually end up with a coset, partitions that are pairwise disjoint and are still cosets? That's the idea. How can we modify this? Because it seems to almost work. There's just one condition that doesn't work. Pairwise disjointness is not guaranteed. So question, how can we modify these partitions to ensure that we end up with a partition that consists of things that are still pairwise disjoint? Well, I mean, what could possibly go wrong here? Well, what could possibly go wrong is that we have some partition gi and some partition pi, which is gih, and some partition pj, which is gjh, such that the intersection is not empty, right? So if the intersection is not empty, then we have a problem because now we don't have pairwise disjointness. But let's ask the question, what does it mean for two cosets to have some element in common, right? So for instance, suppose indeed that pi intersect pj, here I and j being taken to be disjoint, is actually not empty. What would that mean? Well, that would mean that, as seen above, gih intersect gjh is also non-empty. But what does that mean? It means that, what does it mean for these two cosets to be non-empty? Well, it means that there exists some HL, maybe, let's call it, let's pick some symbol we haven't used before, HS, HT, okay. There exists some HT element of H such that, HT, GIHT equals to GJHT. Right. Do you agree with this statement? If we made the conclusion that GIH intersect GJH is actually not empty, well, what would that mean? That would mean that GIH and GJH have at least one element in common. But what does it mean for them to have an element in common? Well, all elements of GIH of the form GI multiplied by some element of H. All elements of GJH of the form GJ multiplied by some element H. If an element is in both of them, what does that mean? Well, that means that there is some HT, element of H, such that GI times HT equals to GI times HT, GJ times HT, right? Does that make sense? Okay. But what does this end up meaning? Well, HT is a group, right? Which means that, well, if you have a group, you have HT is an element of the group H. HT was taken to be an element of the group H. What's so fun about groups? Well, groups have inverses. So we could multiply this, multiply this equation by HT inverse. So we end up with, well, GI times HT multiplied by HT inverse equals to GJ times HT multiplied by H sub T inverse. Okay? When we calculate the multiplication, well, HT times HT inverse just gives us the identity. So now we have GI. All right, let's let's erase this. We want to write things clearly here. So this is now gi. We're saying, look, gi is now actually being seen to equal to well, is this what we really want to say? Let's see. Right. So, I mean, there is no confusion here, right? Because if the left coset gi and the left coset gj have an intersection, they have an element in common. It means that there must exist some ht, right? So far we're good. It means that there must exist some ht for which giht equals to giht, gjht. Right? That seems to follow. Wondering why there is a bit of confusion here. Let's see. Could GIH and GJH have an element in common that's not of this form? Well, clearly not. No, you actually... Oh, no. Okay. Here's the problem. We've made some assumptions that's not necessarily true. Sure. All elements in GIH, right? So all elements in GIH of the form GI... Okay, the pencil got... Okay, let's not bring God into this. Okay. Let's first erase it. So, all elements of are of the form, well, gi multiplied by some element of h. So that means that we could pick an element of gih, maybe let's call it gihs. Okay, gihs is some element of gih. Also, some other element of gih could be, let's say, maybe of gjh would be maybe something like gjht element of uh, gjh, right? This is an example of an element that's in gih. That's an example of an element that's in gjht. To say that these two things have an intersection that's not empty means that there exists some gihs that's equal to gjht. That is, well, that means that gihs equals to gjht for some hs element of h and ht element of h, right? But can we be guaranteed that hs equals to ht? No. And that's why we couldn't just say here that gi times ht equals to gj times ht. We're assuming that the element gi, the element ht for which gi times ht, we're assuming that these elements of h that form the intersection are necessarily equal to each other, and we can't assume that, right? There's no reason to. It could quite be possible that, sure, the intersection is non-empty, but the element here, the element that is the same in both cases, the element that's in the intersection can be written differently in this coset and differently in that one. What we mean by that is if we could find some hs and ht. Okay, so how do we say this? Well, what we're saying is if let's say we could find some hs and ht element of h where hs does not equal to ht, but hs but g but okay, so okay, we'll just let's write it out well. If we can find hs and ht elements of h for which where hs does not equal to ht but gihs equals to gjht, well, it would still mean that this element, whatever it is still in the intersection of gih and GJH, the coset, right? So this element GIS would be in the intersection of the coset GIH and GJH, right? So these HS and HT don't necessarily have to be the same. And we made a mistake here in assuming that they were the same. All right. So to be more correct then, right, we're still looking at our partitions. We're looking at the case, well, so we notice that the problem with doing the partitions is we can't guarantee that the partitions as we have them here will not have non-empty intersection, which means we won't be able to satisfy our third property in order to prove Lagrange's theorem. So we need to fix this somehow. And the way we've been doing the fix is to figure out, first of all, to understand how to fix these partitions so that we get partitions that will work, that will satisfy our three conditions. One thing we might just need, one thing to know how to fix something, we first need to understand what's wrong. So let's try and figure out what exactly is the extent of the problem, is what we've been trying to do. What really happens when GIH and the coset GJH, what does it really mean to say that these two cosets have non-empty intersection, right? What does it mean to say that they're not pairwise disjoint? And that's what we've been studying. And we've said that this means in particular that there exists HS, HT, elements of H, right? HS not necessarily equal to HT. They could be equal, but they don't have to be. There exist HS, HT elements of H such that GIHS equals to GJ HT. But if this is true, well, I mean, there's nothing stopping us. HS is an element of H, and H is a group. In a group, every element has an inverse. So we could multiply this equation here to the right by HS inverse. Now we have GIHS times HS inverse equals to GJHT times HS inverse. This is what we have so far. We end up with GI equals to GI HT times HS inverse, right? Because HS times HS inverse give us the identity. All right. So now it means we've managed to write GI in the form GI. Sorry, did we make a mistake? Yeah, we did. This was supposed to be GJ, right? GJHT. Okay, so this is GJ, right? So far so good. There exists some HS and HT such that GIHS equals to GJHT. We can multiply to the left, to the right by HS inverse to this equation. We end up with this. HS times HS inverse gives us the identity. So now we have HI equals to GJHT times HS inverse. Okay, so far so good. But what does this really mean? If GI equals to GJHT times HS inverse, well, that means that, well, okay, I mean, we're looking at the cosets, right? One of the cosets we're looking at was GJH, okay. Another coset we're looking at was GIH. But if GI equals to this stuff, we can replace GIH by just whatever it equals to. So this coset then is the same as GJ HT HS inverse times H, right? That's perfectly legit. We just wrote H really big because this was kind of large. Okay, right, this coset and this coset are the same because GI is the same as this GJ times HT times HS inverse. Okay, well, but what does this really mean? Well, let's think about what does GJ times HT times HS inverse really amount to, is the question. Okay, let's make sure we've written it down correctly. Don't want any confusion. So we're saying that GIH equals to GJ times HT times HS inverse, all of this, whatever. Remember this, notice that this element, we've written it weirdly, but it's still GI, so it's still an element of the group, and so we could think of the coset when we left multiply this by H. Okay, well, we said that H was just equal to, well, just H1, H2, Okay, we had said it to be 1 equal to 1, h1, h2, up to like some element hr was what we'd said. So let's write this well to avoid any confusion. This is really the scenario we now have. Okay, right here. This is what we have. Okay, well, notice. So what is GIH gonna be? Well, or in particular, if we think of GI as this, what's that gonna be? Well, exactly as you guess it is, right? It's gonna be GJHT times HS inverse multiplied by H. But that's really equal to, you guessed it, GJHT HS inverse, comma, GJHT HS inverse times H1, comma, GJHT HS inverse times H2 all the way up to GJ HT HS inverse times this was HR, right? So that's really what this coset is. If we write GI in this way, GJ HT HS inverse. Okay, well, notice that what we're dealing with here is we're dealing with a group. So in particular, all these elements, all the GIs and H's are elements of a group. So associativity works. This means that we could multiply H2 and HS inverse, HT and HS inverse, HT and HS inverse times H1, HT HS inverse times H2. Maybe let's proceed systematically. So make sure we get this right. So we could rewrite this as follows. See if you agree with this. So this same coset now becomes, well, just GJ, right, times HT. Okay, in this case we've changed nothing, times HS inverse. Sure. Okay. Over here, well, it's associative. Multiplication is associative. So HS inverse multiplied by H1 gives us some element of the group, right? So in fact, we could think of this problem this way. Well, here we have, if we look at associativity, to carry out this multiplication, we first need to, we can multiply HS inverse by 1, get the answer, then multiply it by GJ times HT. Over here, we could multiply HS inverse by H1, get the answer, then multiply it by GJ Over here, we could multiply HS inverse by H2, get the answer, then multiply it by GJ Over here, we could get HS inverse multiplied by HR, get the answer, then multiply by GJ Alright, we've just run out of time. So, let's see. So try to convince yourself that, and we'll continue this in the next video, but try to convince yourself of the following idea, that after all of it is said and done, GJ HT HJ inverse, sorry, HS inverse times H, this coset is really equal to the coset GJ times H. But notice that we said that this GJ HTS inverse, right, we said that over here, we said that GJ HTHS inverse was really the same as GI. So this coset was the same as this coset. So really we're saying that this equals to this equals to this, GIH. See if you could convince yourself of this fact, that in fact GJHTHS inverse multiplied by H equals to GJH, and which makes us conclude that GJH equals to GIH. So, and in particular, think about, well, why is it important that we've been able to conclude that GJH equals to GIH if GJH intersect GIH is not empty? What's the significance of this result? And how does it relate to us proving or think, or how can we use this idea? How can we use the idea that GIH intersect GJH is empty? Okay, let's back up. If GIH intersect GJH is not empty, implies that GIH equals to the coset GJH. How can we use this idea to modify our cosets? Right? Remember, we started with this coset. We started with the cosets. We said that G equal to the coset G1H, G2H, right? All the way till, in this case, I think we had M elements, it was GMH, right? Whatever the cardinality of G was. This is what we'd had before. And we'd said that this partition almost works, but the intersections are not pairwise disjoint. That is, it's possible that, let's say, for some GI and GJ, GIH intersect GJH may actually be non-empty, where GI does not equal to GJ. And we said this was a problem because it's not, the partition is not pairwise disjoint. So, given this information, that if any one of these cosets have non-empty intersection, then it means that the cosets are the same. Given this information, can you think of a way to modify this partition to give us a partition that has the condition that none of the cosets, that none of the partitions have an intersection in common? That is, can we modify this partition to come up with a partition that is pairwise disjoint? And if we can do that, then we'll probably be able to add that to our list over here. Right? So remember, we'd come up with a list of properties. We'd said that if we can establish that each GI is in some partition, each partition is a coset. If we can also establish that for any two partitions, PI intersect PJ is disjoint. If we can establish this, right, is empty. All right. So if we can establish that for any where I does not equal to j, if we can establish this, that the partitions are pairwise disjoint, right, then basically we're done. We'll be able to prove successfully that the cardinality of H must divide the cardinality of G. Right, that was the idea. So could you establish this third condition given what we've done right now? Please do think about that, and then in the next video we'll see how it all works out, if at all it works out. So, but I mean, the big picture of this work has been to prove the following: Lagrange's theorem. Suppose we have a group that's finite, and we pick some subgroup of the group. Is it true that the order of the subgroup must divide the order of the group? This is Lagrange's theorem, and this has been our fifth exploration of it. Thank you very much for listening to. Thank you very much for actually watching this video, and yeah, hope it's been fun. Thank you very much, and have a relentless week. Bye.